everyone. Thank you for attending our Raman Microscopy and Imaging webinar today. Our presenter is Dr. Carlos Murillo, who received his postdoc at the Advanced Industrial Science and Technology in Fukuoka and was research scientist at Kyushu University in Japan, where he lived for several years. Carlos received his doctorate of engineering from Kyushu University and his master's in BS from Simon Bolivar University in Caracas, Venezuela. And he is an application scientist here at JASCO, Inc. So we're going to get started. And Carlos, if you want to begin, please go ahead.
Okay, thank you, Leah, for your introduction. Well, today I'm going to be talking about Raman microscopy and imaging. First, just a few words about JASCO. JASCO is the Japanese spectroscopy company, also known in Japan as Nihon Bunko. The R&D and manufacturing facilities are in Hachioji, Japan. And their founders are the physicists Yoshio Fujioka and Shinichiro Tomonaga, who shared the Nobel Prize in Physics in 1975 with Dr. Richard Feynman in quantum electrodynamics. JASCO was established in the United States in 1972. And we are located in Eastern Maryland. This is like a suite of our spectroscopy and chromatography products. Today I'm going to be talking about Raman microscopy and imaging. I just want to remind you that maybe 3 or 4 weeks ago, Dr. Burgess, James Burgess, also made a presentation about the principles of Raman fundamentals, so I strongly recommend that you watch also that webinar. With that, I just want to go over the presentation overview. I'm going to looking again at the Raman spectrometer schematic, talking why someone is interested in micro-Raman, also some of the JASCO Raman products. And I divided these, the way that I thought that imaging in spectroscopy imaging should be divided is in 2 parts. One is the observation mode that facilitate to take an image, and also the scanning or mapping to create Raman mapping images. So I'm going to be talking about 2 different scanning modes in the JASCO products. One is the fast mapping that we call the QRI, that is the quick Raman imaging. Also the surface scanning image, that is the SSI, and that is recommended for tilted, uneven, or rough surfaces. I'm going to be looking at different features that help to take images and expedite the process of making Raman images. And later I'm going to be looking at different applications of Raman imaging. So this is the schematic of Raman spectrometer. And this was explained in the basics of Raman, but today I just want to emphasize in 3 different parts. I'm going to be looking at the objective lens, sample stage, and the detector. Just to review, the light source in a Raman spectrometer is the laser, and the laser goes to a beam splitter, and in here the light is going to be reflected, then go to the objective lens. It is reflected, and it's going to create the Raman signal, and this Raman signal is going back, and this time it's not reflected, it's transmitted through the beam splitter, go to a mirror, then rejection filter, split, the light then is dispersed in a grating, and then it goes to the detector. So why micro-Raman? Why somebody would like to look at the micro-Raman? Well, the Raman is a micro technique. So this means that actually where the laser is focused. In that same spot, the light is going to be scattered, and that is what we want to actually measure. The Raman microscopes, besides to have the spectrometer, the microscope is using the microscope optics, so that is going to define the sample, sampling area, also the special resolution for the measurement and the imaging. And of course, because it's a micro sample, it's going to require less sample, and at the same time, it's going to produce less fluorescence. And the Raman microscope are a confocal microscope, and in this feature, and I'm going to be showing this in the application, the measurement can be taken under the surface. That means that we can take measurements inside the sample. Also, we can take measurements and create images in 3D. Some of the applications for the Raman spectrometer, one is the semiconductor. We can measure stress and impurities in a semiconductor, which is really important. Semiconductor devices should be stress-free, and they shouldn't have any impurity that reduce the conductivity in the device. Also, the polymer is a very common application. Similar to IR, polymer materials are going to are very sensitive to any shift in the vibration due to the laser light, and they are it's a very common application. Another very common application is the carbon material. They have a very nice Raman signal, so as a consequence, it's very easy to measure diamond, graphite, graphene, diamond-like carbon in Raman spectrometers. Pharmaceutical applications. One of the most popular applications is the imaging of the medical ingredients, especially looking at the distribution of the ingredient all over the surface of, more specific to a tablet, with a more like a quality control goal. And of course, we can look at the different, we can call it crystallinity of the active ingredients. Some active ingredients are crystals, some of them are amorphous, so that's why we include the crystal polymorphism. And geology is a very common technique, and this is one of the advantages of the laser Raman spectroscopy. It is possible to measure the crystal structure and also look into any gas that is included in the mineral. Some of the products and solutions that JASCO provides is the RMP 500, that is our portable Raman, and actually is a Raman Pro. We have our standard model, that is the NRS 4500. High-end models is the NRS 5500, 5600, and the flagships is our series of 7000. Our standard model is the 4500. Most of application can be done in this instrument, but when somebody really needs very specific application, it can go to 5000 or 7000 series. These three models can have the accessory for the QRI, that it has speed imaging system, and this is the focal length, and this is the main difference between this system. The focal length, again, I recommend that you go back and look at the Raman fundamentals webinar. It's going to provide the resolution, spectral resolution of the instrument. These two instruments, the 500 and the 4500, can have only one detector, and is basically the CCD or the EMCCD. I'm going to be talking in few slides about that. They are more for a quality control environment and academia, and we have several applications like microplastic, multi-layer materials, like polymer multi-layer material, carbon materials, impurity, biological samples. In the case of the 5000 and 7000 series, we can add two detectors, either the CCD, EMCCD, or an in-gas detector. And the in-gas detector is more for the near IR lasers, like the 785 and the 1064. And these instruments, especially the 7000, is more for high spectral resolution application and very low wave number measurement. We can go up to 10 or 5 wave number with these two instruments. And for the high wave number resolution applications, you can find that with the stress in semiconductor, also impurities. And I'm going to show some of those examples almost at the end of the webinar. So what is required to create a high definition Raman image? First, you can have different modes. Also, it is required a high pixel camera, auto stage that can move in X and Y and also in the Z direction. They are more popular, these applications nowadays, where large or wide map areas require, so someone can need a fast function, and also for surfaces that they are uneven or rough surfaces, we can have, and this is a product from JASCO, the surface scanning imaging. Of course, after the collection of all this data, it is required to create images, the analysis, and the process of the data. Okay, so some of the observation modes. This is the bright field. The bright field is the most common microscopy technique to take images. The light comes from above of the objective lens or from below. And the main characteristic is that you are going to see a gray area with some contrast or gray, more gray or darker phases. The other observation mode is the dark field. In the dark field, the light doesn't come from above or under, it just comes from it comes oblique. And what we are going to look is the dispersion of the light. And actually, it can reproduce the color of the sample very, very, very well. The only issue here is that some of the dark samples or the dark phases are going to be missed. So we have a mixed observation mode where the bright and dark field are combined, so everything, it can be observed. Now the dark areas here, it can be observed, also the color ones. And actually in this mode, then we can go exactly, since we have an auto stage, we can go exactly where the point we want to make the measurement. And actually, you can see here the Raman spectrum of this yellow particle, or the red, the magenta one, or black. Those are the measurements that we were making with different laser lines. Another observation mode is the polarization. In here, the light, it gets polarized, and of course, if the sample can be polarized, we are going to observe different phases. In the case of this sample, this is just a slight rock sample that is a very common application for geological samples, is the polarized mode. And of course, in the image, we cannot see any different phases, but actually when we apply the polarization in 90 degrees, we can see that a different phase can appear and then make the measurement in those different areas. The last observation mode that I want to show is the differential interference contrast, or very well known as an DIC. And in this observation mode, what it really is important is we are able to see features that they don't appear when the bright light is used. I was before joining JASCO, I was working with failure analysis, and this observation mode was very efficient when I was trying, for example, look contamination in printed circuit boards that sometimes I look at in the bright field and I couldn't find any sign of contamination. Then I was using dark field, and there was no any feature highlighted, but when we use the DIC mode is the moment that I could find some of the features that I was interested, actually contamination. Okay, so the other part that I think is important in spectroscopy imaging is the creation of maps. And these maps are created based on specific vibrational bands. With these, usually the procedure or the methodology that we use is just take an image in a bright field. Then what we do is create an array with different points, and the Raman spectrum is going to be collected at each circle. The sample that you are looking here is microspheres of polymers, and here there are two different polymers. Then when we took the Raman spectra, we find out that the two polymers are PMMA and polystyrene, and then the Raman image is created based on the specific vibration bands of the spectrum that we measure. This is the typical procedure to create a Raman image, even what we call standard or slow speed. But I would like to show the next feature that we call QRI, that is the quick Raman imaging, and this is for high-speed mapping and imaging. In this case, what we're looking here is just the objective lens of the microscope. The laser comes through the objective and is going to take the measurement in the sample. You can see the grid here that is created, similar to what I showed before, and actually in this method, the stage is moving. So this is the configuration for a QRI system. Of course, we need the Raman spectrometer. We are going to have a high-speed stage that is also automated. It can move in X, Y, and Z. And additionally to that, we are going to use the detector that is an EMCCD, and the exposure is recommended to be less than 50 milliseconds. Additionally to these hardware accessories, we need to add other software that is going to help us to create the image. So the conventional, I was talking before about the standard conventional imaging versus the QRI. In this image, we can see this sample is a graphene. On top, we can see the mapping using a conventional imaging. This is a Raman spectrum that looks very noisy. Also, this is the bright field image, and we can see also the mapping that is created live. But with the QRI, we can see that also we have a very clean Raman spectrum. The same bright field image But we can see that the map already has been created. It is much more faster, it's much more clear, and is about 50 times faster than the conventional mapping. So for the standard detector that is used in the Raman spectrometer is the CCD. But in the case of the fast mapping, we need an EMCCD detector. Actually, the CCD detector can run in different modes. One is the EM, that is what we call the electron multiplier. And actually what it's doing is just applying a higher voltage. And then when the signal is registered, those electrons that they are actually being measured in the CCD detector, they are increased. As a consequence, what we have is just an electron multiply signal. It's a signal that is going to increase the intensity of those peaks of interest. So this is the graphene sample. The spectrum on top is showing the G band and D band. Also, we have the peaks down in the spectrum, in the Raman spectrum below. Also, we have G band, D band. But we can see that the image is much more clear and it's much more sharp than the image above. So what is really happening is that, for example, when we have a measuring interval that is similar to the beam spot of the Raman, and this measurement interval is something like 1 micron in the step, and when I say step, is the step that the stage is moving, the image looks really pixel. But if the measuring interval is much more smaller than the spot size of the laser, what we end up doing is collecting a lot of samples, and actually what we are doing is just overlapping the measurement. This, like how you can read here, it's a 0.1 micron step. It's something like 100 nanometers, and is the resolution of this fast high-speed stage. Additionally to that, after we do the measurement, we have a digital filter process. And what the digital filter process is doing is just reducing the signal to noise. So this measurement is done using only the CCD with the standard detector. If it goes really fast, we are not going to be able to register the signal. And actually, when a chloride plus an EMCCD is used, we can see how the images start to be developed. But actually, after when we use the digital filter, the image comes much more sharp. And actually, what it's just doing is creating or enhancing this image based on the information of the image of each spectral band. Actually, what it's just doing is collecting enough information to make these maps with a better edge, reduce the signal, reduce the noise, increase the signal to noise. That is actually what we are doing this step. So this is just an example. When the filter is used, we can see that I'm showing what I was explaining before. We have the signal, and then the digital filter is applied. We have a better spectrum. As a consequence, we can have a better image. And this is what we want to, that is the final goal, to be able to reproduce an Raman image. And the only way to do it is with a very clean spectrum. But if we need to map a large area very fast, we have some challenges, and those challenges are overcome using detectors like the EMCCD, and also a high-speed stage, and some software data processing as the digital filter. Additional to the digital filter, we use the spectral averaging, and this is something that we can enable, and it's just to improve to smooth the data and to have a better signal. In these samples, we have again our PMMA microspheres. The measurement was already done without the EMCCD. We have our peak, then the digital filter is applied, the image is improved, and after that we can do an average of spectrum. And the average is just the average of the spectrum. It's not working in any fashion with the image. With this, we smooth the data improve, and we can get, as a result, we have even better pictures. And this is another example of graphene. We have the G prime band, the G band, D band. These are specific bands for graphene. For those that work with graphene, this is very familiar, but I just want to show this example because we are able to show the bright field image and simultaneously, and at the same time that we are running the test, the image can be created for different bands, and then you can have a map of the whole sample after you finish your measurement. So actually what we do, and the flow chart that in JASCO we use, and maybe is what we are doing, and it can be followed. It's just, we are just taking the measurement, the high speed. We have our spectrum. Then those spectrum can be improved using digital filtration, reducing noise, or doing spectrum averaging. And also we can reduce or correct the fluorescence. And additionally to that, we can use different chemometric techniques like MCR, that is the multivariate curve resolution. Also, you can use PCA, that is the principal component analysis, and spectral correlation. All these techniques are very well known, very well established. I'm mentioning today, but this topic of creating images using chemometric technique is very, very, I think it would take me a long time to make an explanation of this, and I think, I think the best is to have a webinar dedicated only to chemometrics. So please, I'm going to save that for that moment. But actually, something that I really like to use MCR, and for those that they are familiar with chemometrics, is that MCR is one of those techniques that doesn't need any input. When I say input, is just we have to know what are the concentration of the ingredients. So instead of that, the MCR is able to create these maps only with the information after the measurement. And this is something that we can do and is automatically done. The PCA is a technique that is used mainly for clustering and grouping, and also you can use it to create these images at the same as the spectral correlation. But in my opinion, the technique that is very efficient, is easier, and is for novice users, MCR is one of those techniques to go. Okay, so we look at the fast mapping for wide areas. Now we are going to switch gears to the surface scanning image, and this is more applicable to tilted or uneven or rough surfaces. So actually what we are doing in this with this application It's just changing the height of the stage while the measurement is done. But the way that we do it is we are going to make a register what is the topography of the sample, and after that the measurement is done. And actually this is the methodology of the SSI. What it's doing is the data is collected in this red spot. The Raman signal is collected there. Then the stage is going to lower. It's going to take it in the next measurement spot. Then it's going to raise it, and it's going to take it in the next one. But the way that that is done is with a feature that we call all in focus. And actually what we are doing is just stitching all the images. And the stage is going from 0 microns. In this example, it goes from 0 microns to 250 microns. And actually what the stage is doing is moving. And when the sample is focused, it's going to take an image there, and it's going to move to the next place. And when the sample is focused, it's going to take an image to finally stitch all the image, and we can see a 2D image, or we can create a 3D. So when we take the Raman spectrum or the imaging of surface that it have these topographies, you can see that if the stage doesn't lower, we can see that here is focus. It can take a very well defined image in this area. In this area, because it's not focused, it's going to be blur, and then at the end, it's not going to be perfectly focused. But in the case of SSI, what it's doing is just taking the spectrum, the stage is going to lower, and you can see the difference is all in focus, is all optimized to get a good spectrum. As a consequence, it's going to have a good image. So the two scanning modes, before I show the observation modes, you can take images and you can take points of sample, a specific point, and take the Raman spectrum there. With the scanning mode, you can have a grid and collect the spectrum of each grid. We have the option to do it in a fast fashion that is called QRI. We can do it slower if the surface it have certain topography, and all is going to at the end have a very nice image. Some of the JASCO imaging features. These are just features that I was putting together this webinar, and I thought that this is very helpful. We have what we call the focus nav, that is just the autofocus. And if sample is placed in the instrument, the first objective lens that we are going to find is the 5x. And this is, we can think about it of a rough focus or a rough autofocus just to start our measurement. The next feature is called View Nav, and this is just going to help with the auto alignment, the auto light adjustment, and especially it's very effective when we go from 20 to 100x. When we switch, everything is going to be optimized, the gain of the camera, the light, and for those samples that they are really difficult to find, those two features that I show, autofocus and then the auto line adjustment, is very helpful to find those very challenging sample or sometimes powder or particle. The sample search function is other features that we have, and I really like this feature, especially for samples that they are like dust. microparticles, microplastics, the software automatically is going to identify whatever is recognized as a possible sample. The samples can be rectangular or circular. They are going to recognize, then they are going to register. And in this registration, you can, the user can decide whether or not take the measurement. And finally, something that is really useful, if the user upload a database by itself or using JASCO or Raman database, the software is going to automatically identify the particles. And we can do this simultaneously, exactly when you are measuring doing the measurement of these particles. Some of the particles parameters that we use is the third NAP, and in these particle parameters, there are different parameters that can be refined, like the size, circularity, the color. It comes from RGB, or the brightness, the contrast. For those that have worked with particle, if you don't assume the particle is it have a circular shape and it have an oblong shape, you can use two different diameters. One is the ferrite. You can measure in vertical or horizontal. For these applications, for these parameters, we can have up to, I'm just showing like 5 here, but it can go up to 16 different parameters. Of course, you can select which samples to measure. Here are the small features, the small particles. Also, you can decide only to measure the large particles. The IQ frame of location of the measurement is just in this accessory. We use a sample holder with relative coordinates, and these coordinates, what we have here is just the sample. With these relative coordinates are saved in the file where the measurement is done, and actually it can be used to measure the same position in a Raman instrument, also in a FTIR microscope. And we can measure the same location either in the same Raman instrument or go to the other instrument. And we have the possibility to measure the same sample at the same location in a micrometer size at different times. This is an example of the combined measurement of IR and Raman. And in this sample, we can see that we have some polymers, also some proteins, and the carbon is detected when the Raman is used. So finally, some of Raman imaging applications. We have this wide area imaging for a pharmaceutical tablet. This tablet measure 10 millimeters in diameter, and actually it was done using the QRI, that is the fast mapping. All these measurement was done using something like 32,000 different points, and of course the EMCC detector it was used to collect the data. Also, here are the components of this tablet, and it was used MCR to create this map. Again, QRI is used because it can increase the speed of the testing, and this measurement, it was collected in something like 15 minutes. The same measurement can be taken in several hours if it's only run in a standard mapping mode. The other application, as I mentioned before, is the carbon material. So in this case graphene. Here are Raman spectra of different Raman of different carbon materials, and these materials can be either measured or image using Raman. This technique in this application, we can see the silicon carbide wafer that is getting more and more popularity. And in this application, what we did is just to measure one contamination or one precipitate. And it's really interesting how in the Raman, and this is specifically for applications with high spectral resolution, we can see that the Raman spectrum is very similar. They are very close. But when you really have a very high resolution instrument is when you can see the difference between the two spectrum and actually determine that that precipitate that you see there is just a defect in the silicon wafer. The other application is for the stress evaluation using Raman, and actually using the Raman and using like the calibration in this case of silicon, we know that any change to the right or the left, it can represent a compressive stress or a tensile stress if the variation goes from, even we are talking about one wave number, it goes from minus 0.2 to plus 0.2 wave number. And actually we can see how all the compressive stress, it can be either measured or mapped, and the whole compressive stress is present in the corner. For biological samples, we have here a coral crystal polyform distribution. We have the coral crystal, and it has two representation of the coral. One is aragonite and the other is calcite. But it's really interesting that both Raman spectra, they look very similar. But when we go to the low wave number, even close to 50 or 200, we can see that they are different. In another application is the sample hidden imaging analysis. We can, in this case, the sample that we're using is a laminated ceramic capacitor. These ceramic capacitors have different layers, and one is a perovskite and the other is nickel. So when the temperature is increased, what is really interesting is that the crystalline structure is changing. And of course, it will produce a failure in this type of ceramic capacitors. So what it was done is to increase the temperature, make the Raman measurement, and actually the technique of PCF, the principal component analysis, was used to classify the data and actually find out how to create groups of these points. And it was found that actually at different temperatures there was a discrete difference between the crystalline structure. The last application that I have is the 3D imaging, and this is an example of embedded materials in polymer. In this case, we have titanium dioxide with the unattached phase and silicon. This is the spectrum that was taken, but actually we can have either a 3D image with the location of the particles, or we can create a 3D image slice of the sample. With this, I just want to finish reinforcing the idea of analyzing and processing the data after the measurement. And one of the techniques is the MCR, as I mentioned before. And in this measurement, what it was just taking, the measurement was done, as I was mentioning before, creating a grid. And after that grid was created, nothing was needed to first determine that there are 3 different components, and those 3 different components can be mapped in the image. So, and I think, like, again, this is a technique that I'm going back to explain this, but in maybe a fully dedicated webinar. Okay, I think with this, I just want to thank everybody. I just want to invite you again to follow our educational resources. We have more upcoming webinars. One is for our first SSC Theory and Applications webinar. This is for our chromatography instruments. After that, we have an FTIR and microscopy webinar. Please visit our website. We have ebooks or tip and tricks poster. If you want your poster, you just can email us. We can email you the poster, or we can send you a printed poster. You can check the knowledge base to see all the articles that are using JASCO instruments, and please check in ResearchGate that we have circular dichroism spectroscopy ebook there that you can freely download. Next webinar is next week, as I said, is in SFC Theory and Application with Mr. DJ Tagnarelli, that is our application scientist for chromatography. Okay, with this, I just want to finish. I just want to remind you that everybody's going to receive a copy of the slides, also a link with the recording, and also now we are open for questions. Yeah, we have a question like, what is the bottom line of the QRI mapping? How important is a stage in the QRI? How much time takes to map 100,000 points area? So the bottom line of doing the QRI is to create an image of, especially for a wide area like the tablet that I show. And if you're interested to look what is the distribution of the active ingredients of pharmaceutical tablets, that is really important for at least the application that I have worked. It's very important for the pharmaceutical companies because you want to check if there is any agglomeration of the active ingredient, or if you want to see where the amorphous of the crystalline ingredient is dispersed in the surface of the tablet, and see if it's homogeneous. Also, how important is the stage in the QRI is very important. It needs to be a manual, automated stage. Also needs to have small steps like 100 nanometers, and how much it takes to 100,000 points. It depends on the time that you are using to collect, but for example, for that tablet that I showed there, that it is like 32,000 points, and the collection time of each point was 20 milliseconds. It takes something, for 32,000 points, it takes something like 16 minutes or 15 minutes. Okay. There is a question, what are the laser wavelength options? We have several wavelength options. The standard that we use is 532. Also very easy to put the 785, 457. Also we have 405. We can go to the UV. also go to the near IR 785 1064. So if you check the previous webinar, you are going to find that there are several lines. How do you deal with fluorescence for carbon? I guess it's carbon and diamond materials. We have different features to control the fluorescence. One, we have a patented software that it will deal with the fluorescence. Also, for the high-end instrument, we have a feature called double special filtration that we put two sleeves, pinholes, and that is going to reduce the fluorescence a lot. Yeah, so there are different ways to do it. How can Raman give more information than other techniques with graphene? Well, that is a very good question. I'm familiar with the measurement of graphene using the Raman. I haven't studied graphene with other techniques. Oh, what is the temperature for the heating cooling state? We have different models. It can go to room temperature, below room temperature, up to 600 Celsius degree, and the high temperature could be 1500 Celsius degree. Can JASCO system perform surface enhanced Raman spectroscopy on biological samples? Yes, we can use SARS. And SARS, what is really important is just the substrate that you're using. Actually, the substrate that we use, and it's the substrate that mostly is, we use substrates that they are commercially available, and actually they are using gold nanoparticles, and that is what we use for SARS. It says, can a quantitative analysis be performed with this technology, and can the distribution of API on a tablet be quantified? The first question is yes, because we have a suite of chemometric package, and then we have 5 different algorithms to use to quantitate the components. We can use CLS, PCR, and ILS. And PCA, we use it mostly for imaging, and MCR for imaging. So yeah, definitely we can find what is the quantitate the IPA, and also we can look into the distribution of the tablet, quantify. This is something that I was asked before, and yes, we can help you with that. What's the smallest spot size, step size, and spatial resolution? The step size that we have is 100 nanometers. With the auto stage, spatial resolution is going to be determined on the laser that you're using for either 532, 785, but you know that there are some restrictions, physical restrictions for that. And the smallest spot size, I think, if I remember well, we are talking about something about 3 micrometers or lower than that. Well, Leah, I think that are all the questions that I have in the panel.
Yep, that's all the questions we've got coming in right now. If you guys have any more questions, please feel free to visit our website at jascoinc.com. And as Carlos mentioned before, we'll be sending out the PowerPoint slides and a copy of the presentation as well. So thank you, Carlos. And thank you everyone for attending.